We now start module 3 of chapter 2, and we will be talking on spanning set of a vector space. You have learned what is called a linear combination of vectors, and now we will see that we are interested in some spatial subsets of a vector space which in a sense generate the whole vector space through linear combination. Let V be a vector space over a field F and S a non-empty subset of V. Let us define what is called span of S. Usually we use that particular symbol to denote span, which is nothing but the set of all linear combinations of vectors of S. Let us recall that if V1, V2, Vn are finitely many vectors in the vector space V, then a linear combination of V1, V2, Vn is nothing but A1 V1 plus A2 V2 etc. so on up to An Vn, where A1, A2, An are elements in the field F. So, the span of S is nothing but the collection of all such linear combinations of vectors, where the vectors are coming from the set S and the scalars are allowed to vary freely in the field F. A set S is said to be a generating set or a spanning set of the vector space if the span of S is nothing but the whole vector space V. You can see that S being a subset of V and V being a vector space, span of S is surely contained in V. Now, when this containment becomes an equality, that is when we call S a generating set or a spanning set of the vector space V. Now, the question is, why are we giving some spatial name and calling some set a spanning set? Because it is obvious that V itself is a spanning set of V. V is a vector space, therefore, it contains all possible linear combinations of vectors from V. So, surely we are looking for some subset of V which is possibly not the whole of V, but something smaller, in fact the smallest such. And what do we mean by smallest? We mean that in the sense of set inclusion. Let us go back to those classical examples. R3, which is a vector space over the real field. Now, this particular set, that is the set containing 1 0 0, 0 1 0 and 0 0 1, is indeed a spanning set of R3. Well, it is easy to see because a typical element in R3 would look like A comma B comma C, a 3 tuple, and that can be written as A dot 1 0 0 plus B dot 0 1 0 plus C dot 0 0 1. Therefore, it is indeed so that these three spatial vectors span the whole vector space R3. One more example, the example of collection of all 2 cross 3 matrices with real entries. Again, we have a very spatial subset, namely the set containing these 6 matrices, and you can see that these matrices have only entries 0 or 1, and the speciality is that the position of 1 is changing for each one of these and the other places are being filled with zeros. Well, this again spans this vector space for the simple reason that if you take a typical element from this vector space, then it would be a 2 cross 3 matrix, and it is not difficult to see at all that 2 cross 3 matrix can indeed be written as a linear combination of these 6 matrices. Again, the old example of collection of all polynomials with real coefficients whose degree is at most n. Now, if you look at these n plus 1 polynomials, in fact monomials, namely 1 x, x square and so on up to x to the power n, then each one has degree at most n for sure. And what is important is that any polynomial whose degree is at most n and having real coefficients can be expressed as a linear combination of these monomials. So, again we have a spanning set for the vector space Rn x. Let us now see the span of S a little more closely. The theorem says that if you have a non-empty subset S of a vector space V over a field F, then span of S is a subspace of V. Span of S is the smallest subspace of V containing S, and span of S is the intersection of all the subspaces of V which contain S. So, these three propositions in fact characterize span of S comprehensively, in the sense that span of S is nothing but a subspace, and not just any subspace, but the one which contains S and also the smallest one which contains S. So, again smallest in the sense of set inclusion. Let us see how to prove this theorem. Let us prove the theorem. Let us recall that we had this special 0 in boldface, which is the additive identity of the vector space V, and the usual one is the additive identity of the field F. And we know that 0 dot x is 0 vector for every x in S. This shows that the 0 vector is in span of S, and therefore span of S is non-empty. Now, if x and y are vectors in S and alpha beta are in the field F, then alpha x plus beta y belongs to span S, because span S is nothing but the collection of all possible linear combinations of vectors from S, and alpha x plus beta y being a linear combination of x and y is indeed in span of S. Therefore, span S is a subspace of V. Now, we are trying to show that it is indeed the smallest subspace of V containing S. First of all, why is it so that span S contains S itself? Well, any vector x in S is of course 1 dot x, and therefore it is a linear combination which shows that S is also contained in span of S. Now, suppose that W is a subspace of V which contains the set S. If we can show that W contains span of S, then span of S being a subspace itself containing S has to be the smallest one in the sense of set inclusion. And why is it so that any subspace W containing S must contain span of S? Is because W must contain all the linear combinations possible from S, because W is a subspace itself and it contains the set S. Now we come to the third part, and we show that span of S is nothing but the intersection of all subspaces which contain S. Why is that so? So, suppose X is a vector which is in the intersection of all subspaces containing S. That means X is a vector which is contained in every subspace containing S. Therefore, it is also contained in the span of S, since span of S itself is a subspace of V containing X. Therefore, span of S has to be the intersection of all subspaces which contain S. You have learnt the definition of a spanning set of a vector space, and you have also seen a theorem which in a sense characterizes the spanning set, or the span to be precise. But what is really difficult is that given a vector space V, how do we find a spanning set or a generating set S? Or if I have a subset S of V, how do we understand, or how do we prove or disprove that S is a spanning set of the vector space V? Well, we will be able to answer these questions comprehensively, but for the time being, let us see at least one example and try to compute a spanning set. Let us understand the spanning set and the span through an example. Consider the vector space R3 over the field of real numbers and the set S, which consists of these three vectors, namely -2, 0, 3, 1, 3, 0 and 2, 4, -1. Let us first see what span of S is. So, span of S, which is nothing but the collection of all possible linear combinations of vectors in S. That means it is the collection of all these vectors that you see over there, that is -203.A plus 130.B plus 24 -1.C, where A, B, C are elements from the field of real numbers R. Now, you know that 1, 0, 0, 0, 1, 0 and 0, 0, 1, they span the vector space R3. So, it is quite natural to ask whether these vectors belong to this span of S or not. You can see that we have a system of 3 linear equations in the unknowns A, B and C. Well, what is this system of equations for? We are first trying to understand whether the vector 1, 0, 0, the first canonical basis vector, is in span of S or not. Let me go back to the previous slide once. Span of S is the collection of such vectors minus 2a plus b plus 2c, comma 3b plus 4c, comma 3a minus c, where a, b, c are varying in the set of real numbers. So, if you want 1, 0, 0 to be in span of S, that would mean that minus 2a plus b plus 2c should be 1, 3b plus 4c should be 0 and 3a minus c should be 0 for some choice of a, b, c in R. System of equations E1. So, now the question is, can we solve this system of equations for the unknowns A, B and C? If we can solve, then 1, 0, 0 belongs to the span of S, and if we cannot, that would prove that 1, 0, 0 does not belong to span of S. Well, it is simple enough to see that the third equation implies C equal to 3a, and then the second equation shows you that 3b must be minus 4c, and C being 3a, 3b has to be minus 12a. Therefore, b is minus 4a, and if you substitute back b is equal to minus 4a and c is equal to 3a in the first equation, then you get 0 is equal to 1, which is of course impossible, which shows that we cannot have real numbers a, b and c which satisfy this system of equations E1 simultaneously, and therefore 1, 0, 0 does not belong to the span of S. Now it is time to see whether 0, 1, 0, the second canonical basis vector, belongs to span of S. So, this question naturally gives rise to this new system of equations denoted by E2. Again, if we can find real numbers a, b, c such that they satisfy this system E2 simultaneously, then we indeed have 0, 1, 0 belonging to span of S. If you look at the third equation, then you get C is equal to 3a, and if you substitute it back to the second equation, then you get b is equal to 1/3 minus 4a, and if we substitute all these back to the first equation, it yields 1/3 is equal to 1, which is again impossible. Therefore, 0, 1, 0 does not belong to span of S. Now we see that 0, 0, 1, the third canonical basis vector, also does not belong to span of S. You see the system of equations E3, which if you can solve for real values of a, b and c, then 0, 0, 1 would belong to span of S, otherwise It would not. Once again, the third equation gives you that C is equal to 3a minus 1. And then if we substitute it back to the second equation, you get B is equal to minus 4a plus 4 by 3. And the first equation gives you minus 2 by 3 is equal to 0 if you substitute back these values of B, C, etc., which is of course impossible. Therefore, 0, 0, 1 does not belong to span of S. So, now it is quite interesting to see that 1, 0, 0, 0, 1, 0 and 0, 0, 1 span the whole vector space R3, but span of S, which is sitting inside R3, which is a subspace of R3, does not contain any one of these. Now, how do we understand span of S? Can we understand it geometrically? Let us first see what are the vectors which are in span of S. If you recall, span of S was the collection of all 3 tuples of the form minus 2a plus b plus 2c comma 3b plus 4c comma 3a minus c. If a vector x, y, z belongs to span of S, then we should be able to write minus 2a plus b plus 2c is equal to x, 3b plus 4c is equal to y, and 3a minus c is equal to z. If we eliminate b from the first 2 equations, we get 6a minus 2c is equal to y minus 3x, and the third equation gives us 6a minus 2c is equal to 2z. If we equate the expressions obtained for 6a minus 2c, we get 3x minus y plus 2z is equal to 0. You know what this is. 3x minus y plus 2z is equal to 0 represents a plane in R3 passing through the origin 0, 0, 0. And we have actually showed through this computation that span of S is contained in that plane 3x minus y plus 2z is equal to 0. So, it is natural to ask, is this exactly equal to that plane? That means, is the containment an equality? A typical point on the plane 3x minus y plus 2z is equal to 0 indeed looks like S comma 3s plus 2t comma t for some real numbers s and t. Well, you know why is it so? Because 3x minus y plus 2z is equal to 0 implies y is equal to 3x plus 2z. Therefore, you have liberty to vary the first and the third coordinate freely, and automatically the second one is fixed, and that is what you see in the expression s comma 3s plus 2t comma t. Now, our aim is to see whether a point of this form, that is s comma 3s plus 2t comma t, belongs to span of S or not. That means, can we get real numbers a, b, c in terms of s and t such that they satisfy this system of equations E, which is minus 2a plus b plus 2c is equal to s, 3b plus 4c is equal to 3s plus 2t, and 3a minus c is equal to t. If we eliminate C from the last two equations, we get 4A plus 2B is equal to S plus 2T. Therefore, one solution for ABC in terms of S and T, which can be obtained by inspection, is that A is equal to S by 4, B is equal to 2T and C is equal to 3S minus 4T by 4. And of course, S and T being real numbers, A, B, C are real numbers as well. This shows that a point which is lying on the plane 3x minus y plus 2z is equal to 0 is indeed in span of S. Therefore, the span of S is nothing but the plane passing through the origin, which is given by 3x minus y plus 2z is equal to 0. So, what is that we have seen? We have seen that span of S, being a non-trivial subspace of the vector space R3, contains none of the canonical basis vectors of R3, which is the first interesting observation. And then we have seen that span of S geometrically represents a plane passing through the origin, and the equation is right in front of you. Now it brings us to this very important question: is S the smallest spanning set for 3x minus y plus 2z is equal to 0? What is that supposed to mean? Well, points x comma y comma z which satisfy 3x minus y plus 2z is equal to 0, you know that they do form a subspace of R3, because 3x minus y plus 2z is equal to 0 is a homogeneous linear equation, and solutions of any homogeneous system of linear equations do form a subspace. Therefore, it is quite natural to ask whether some spatial set like S, a spanning set or not of this subspace, which is nothing but a plane passing through the origin, and again smallest in the sense of set inclusion. This brings us to the end of the third module of chapter 2, where we have discussed spanning set. Now, what is interesting is to find the smallest spanning set of a vector space V, smallest in the sense of set inclusion, and we will see that smallest spanning set is indeed spatial for a vector space.